Hello everybody, this is Shane with the Yoon Group, and today I'm going to show you how to prepare samples for cyclic voltammetry and how to probe for catalytic oxidation using cyclic voltammetry. So I've got two samples here. One is one of my substrates and one is ferrocene, which is my redox mediator. And I've already prepared my electrolyte solution or diluent, but now I have to prepare stock solutions and then working solutions for the things that I'm going to use. So I'll do that now. You want to make sure that your electrolyte solution is well mixed. So I've already done this before, but it doesn't hurt to just invert it a few times to make sure that it's nice and good. Take a 10 ml volumetric flask and transfer your sample to it. And of course, you don't want to contaminate the diluent, so use a separate pipette to add uncontaminated diluent to your vial, just so you can get a quantitative transfer. I usually do it 3 times. And that should get almost all, if not all, of the sample transferred over into this volumetric flask. And now you want to just dilute to the line that you have marked on there so you can know the concentration. I weighed the samples out beforehand because I'm pretty confident that you guys know how to use a balance. And you just want to fill up to the line. It's okay if it's not absolutely perfect for these cases, but if you were doing hardcore analytical chemistry, it would become more important to be more accurate. So I've got my first solution prepared. This is going to be my stock solution of the substrate. I just invert it a few times to mix. And then I label it so that I don't forget what this colorless liquid is. This is my stock TMS substrate. All right, and then I'll make one of my working solutions just so you can see how to do that. For that, you're gonna want your stock solution and a volumetric pipette. So this is already mixed because I just mixed it. And you'll just pipette up a little bit beyond the marker line of your working solution, and then I usually just pop the bulb off and cap it with my thumb and wipe off the tip so that you don't have any excess, because these are to deliver pipettes. And then you just ease off the end with your thumb a little bit until the solution gets to the line. There it is. And then deliver that to your volumetric pipette. Allow it to deliver completely, but you don't want to go too crazy. You don't want to try to get rid of that last little bit, because these pipettes are designed to deliver exactly 2 mils. So I'll set that aside. And now I can dilute this to volume. Should cap my solutions first, since I'm not currently using the stock solution. Invert this a few times to make sure it's still well mixed. And then I'll dilute this solution to volume as well. That's good. Just pipette the excess away. Set the diluent aside. cap my working solution and invert it to mix. Best practice is to invert it 10 times. Usually that's not too bad. And of course I will label this as my working substrate solution. So that is essentially how you do serial dilution for the preparation of these working solutions. I'll do that again with my ferrocene and then create a working ferrocene, and then I will pipette 2 mils of the stock ferrocene and the stock substrate to create the mixed solution. I'm going to do that off camera though, because I trust that you can imagine how that looks. All right, I've got my 3 solutions created, and I am ready to start taking CVs. So I will add one of my solutions to the electrolysis cell. Usually just about half of the solution is totally fine. And then I will polish the electrodes. So the glassy carbon working electrode needs to have a silica polish before you use it. So just wet the pad, it should already have plenty of silica on it, and polish in a figure 8 motion. That creates a nice uniform surface. Rinse off any silica, and then rinse off with your solvent of choice, which in my case is methanol. And just shake it to let it air dry. You don't want to disturb the nicely polished surface that you've just created. And then insert the electrode into the cap that puts it into the solution. And you can see that the electrode is well below the surface of the solution, so that's good. The silver counter electrode, or sorry, the platinum counter electrode does not need to be polished, so you can just insert that directly. And then the reference electrode needs to be in its reference solution, which I have here for methanol. The reference solution is going to be stored in, or sorry, the reference electrode sheath is going to be stored in a solution that doesn't have any silver nitrate. So you're going to have to get rid of that and add the actual reference solution. So pipette the storage solution back into the storage container. Pipette some of the reference solution into your reference electrode sheath. Then you can insert the reference electrode into the solution. Add this O-ring, which will help to keep the reference solution from hitting the bottom. And then insert that into the cell as well. And there we go. We've got the prepared cell. We're ready to go over to the potentiostat. And I actually don't know how the camera looks here, so I'm going to take a minute and fix that and rejoin you shortly. Okay, it looks like the camera looks okay, so we're ready to put the cell into the little holder and attach the electrodes. Well, but first before I attach the electrodes, I'm gonna start sparging, because you want to sparge it for at least a minute to get rid of any excess or any dissolved oxygen. Otherwise that might interact with some of your substrates or just obscure peaks or just look ugly. So I attach the red one to the working electrode, the green one to the counter electrode, and the white one to the reference electrode. I apologize if the camera is not the greatest. I'm doing my best. Alright, so I'm gonna let that sparge for a minute. While I'm doing that, I'll start a new folder for this experiment. I happen to already know what it's called because I made it already. And then I'll start a new cyclic voltammetry experiment. And I'm gonna set up some parameters that I already know what I want. If you are interested in trying to figure out like what you would use in this case, I encourage you to check out my flash talk on cyclic voltammetry, because I go through some of how to select parameters and like what are the most reasonable ones. Typically, I'm just using parameters that I know will work. So I'm going from negative 500 millivolts to 300 millivolts versus the reference. And actually, I don't even need to go that high. I'll just go to 200 millivolts versus the reference. And that should fully capture the ferrocene wave. You know what, I changed my mind. I'm gonna go I'm gonna go up to positive 500 millivolts because I don't know exactly where the substrate will be. So we're gonna find that out first. And we're really only caring about the first oxidation wave of the substrate. There will be more, but typically we only care about the first electron transfer for the project that I'm working on. So I think this has been sparging for at least a minute, so I'm gonna not fully withdraw the nitrogen line, but just leave it in the top of the cap so that it's under positive nitrogen pressure. Make sure that none of my wires are touching any metal. They are not, so I'm ready to perform. So this might be hard to see on the video, but I'm sweeping from negative potentials to positive potentials. You can see now that there is a oxidation wave and a second oxidation wave, and then it's leveling off, and then there's a third oxidation wave, which is much bigger. So really I only needed to go to about, well, 0 volts versus the reference to capture the first oxidation wave. So I think I'm actually gonna do that. So, all right, the experiment is complete. Looks all right, but I really only care about this first one, so I'm just gonna make another experiment. I don't think that the electrode has been passivated too much, just from previous experience with this substrate. So I'm not gonna worry about polishing it again. Best practice would be to polish it again, but sometimes you can get away with not doing that. I'm just gonna change the vertex potential to be 0 millivolts, which, let me double check. Yep, looks pretty good. And then I'll go back and just run it again. So it's starting at negative 500. And it's going. The first oxidation happens, starts at about negative 200 millivolts, and then it stops. And so we don't see a reversible wave in this case because there's a follow-up reaction that decomposes the substrate after it's oxidized. But we can see here now we've captured the first oxidation wave pretty well. I'm gonna run another CV for ferrocene. I will rejoin you when I have that solution prepared. Just kidding, I'm rejoining you early because I want to show you how to clean the electrodes between solutions. So you just take them out of the holder, rinse them off with the solvent that you're using. In this case it's methanol. And then you can go ahead, well, I should have done this first. You can insert the solvents, or you can insert the electrodes into the next solution just so that the reference doesn't dry out. But you want to remove the working electrode so that you can polish it. Okay, so now the reference and the counter electrode are sitting in the next solution. That's going to be the working ferrocene solution. I will just quickly polish the working electrode again. Rinse it off. Rinse it with your solvents. Let it dry so that you're not changing the concentration, even though a little bit of methanol isn't really going to hurt anything. All right, now we're back here. We're going to go sparge again. Get in there. There you go. And set up our electrode connections again. And nothing's touching metal, there's no short circuits. Also, I would recommend, while this is sparging, to rename your experiments so that you know what it is. So this is working TMS, -500 to, I forget what I went to, I think it was 500 millivolts. Let me double check that. Yep. And then this other one was working TMS, -500 to 0 millivolts. Great. So now for the best comparison, I'm going to want to do the 3 different solutions at the same sweep width and sweep rate. So I'm not going to change anything this time for the CV parameters, even though I'm working in a different solution. And hopefully I should capture the entire wave of the ferrocene oxidation and reduction. Pretty sure I will, but we'll see. Just gonna let it sparge for a little bit longer. Not too worried about oxygen in the presence of ferrocene, especially because I'm not going to very negative potentials, but it's always best practice to sparge. I think that's sufficient. Again, pull it out of the solution, but not out of the cell completely, and we will perform. And I'll try to get a better shot of the computer this time. So we're sweeping from negative to positive. There's the first oxidation, and it peaks and comes back. And this one will be reversible, so we'll see the reduction wave as well. Perfect. All right, so there's our ferrocene scan. And if we compare the two, the TMS caps out at about 12 microamps. The ferrocene caps out at about 20 microamps. So in the mixed solution, if we don't have any electron transfer, we should cap out at about 30 microamps, just because it'll be the sum of the 2 oxidations. And they should be discrete. They should be, you see the peak of this one is at about -100 millivolts, and the peak of the ferrocene is at about -150 millivolts. So you should still see both of those discrete peaks. And if there's no electron transfer, you should see the full reduction wave of the ferrocenium as well. But we'll see what happens. I'm not gonna make you watch me prepare the next solution. I'll just rejoin you when we're ready to take the CV. All right, we're back and we're ready with the final solution. It has been sparged, and let's take the CV and see what it looks like. Same start as the others, flat line, and then around -200 we'll see the oxidation. And that doesn't look like 2 discrete peaks. And that reduction looks a little smaller. So this definitely doesn't look like necessarily the sum of the 2, which Alright, I apologize for the interruption. The battery of the GoPro died, but we're almost done. So this is what the mixed solution looks like. I've gone ahead and taken screen captures of each of them so that you can compare them side by side. This might be a little hard to see on the GoPro, but I've first got the substrate, and then the ferrocene, and then the mixed solution. And you can see that in the mixed solution, there's not really a discrete wave for the substrate oxidation at all. You do still see the ferrocene oxidation, and actually the current is slightly higher than the sum of the 2 at this potential. You can see that at this potential of about 150 or -150 millivolts, the substrate is at about 4 millivolts. The ferrocene is slightly below 20, but the mixed solution is higher than 30. That suggests that there's electron transfer happening. And similarly, I apologize for the legend covering this up, but the reduction wave of the ferrocene, and ferrocene just by itself is about -10 microamps. I might have said volts before, I apologize if I did. But the mixed solution has a lower magnitude of the reduction wave at about -5 microamps. So that also has suggested that there is some of the ferrocene that once it's oxidized, it's consumed by something else, and that's what it's consumed by is oxidation of the substrate or electron transfer. So we have pretty confidently established that between this substrate and ferrocene, electron transfer does happen, which is what we expected and what we hoped for. So now I think that the reaction that I want to run should work. And this should wrap up the mini tutorial of how to run a CV and probe for catalytic oxidation. Okay, bye.